So remember that we've been talking about polynomial operations. We did addition, multiplication, and subtraction, and then we looked at our two different types of division, so both synthetic and long division. And now we're going to look at kind of what the graphs of polynomials look like, and then also some of their characteristics. So the first thing that we need to go over is a polynomial function. So remember that when we start to look at graphs of things, we need it to be either y equals or f of x equals something with another variable in it in order to be able to graph it. So in this case, when we're looking at a polynomial function, we are looking at a continuous function . So remember, by continuous, I mean that when we start our graph, if I put my pencil on the first part of the graph, I can draw the entire graph without having to pick my pencil up. I'm not going to have any holes or breaks in my graph. And by a function, it means that it has to pass our vertical line test. So a continuous function described by a polynomial. So remember that our polynomial had the definition that it had to have real number coefficients and positive whole number exponents. And it can only have one variable. So technically, just a general polynomial could have multiple variables. We looked at a couple of examples like that. However, when we're graphing them, they can only have one variable. So first, let's start by evaluating some functions. So remember, we are looking at polynomials. So in this case, it's going to be w of x. So remember that the letter in front is kind of the name of the function, and then the variable inside of the parentheses tells you what variable it's in terms of. So a lot of times we'll see f of x, but we can also see g of x, r of x, r of t, whatever the two variables are. That's how we label the function. So in this case, we're wanting to find w of 5 and w of -4. So remember that when we're finding or evaluating a function at a specific number, we're just going to replace all of my x's with the number that we are replacing it with. So in this case, it's 5. I'm going to replace anywhere that I have an x with a 5. So simplifying that, 5 to the 4th times 2 is going to give us 2 times 5 to the 4th is going to be 625. Well, since 5 to the 3rd times 5 is really just 5 to the 4th, we will just get 625 here. 5 squared is 25 times 3 is going to give us 75 minus 10 plus 8. Then combining all of those together, we should get 698. Alright, next up for part B, this time we're looking for w of -4. So again, just replacing all of my x's with a -4. We are going to need to be careful with that negative, because remember, when we plug things into our calculator, it does not automatically square a negative correctly. So if I've typed in -4 and then just put a squared out to it with no parentheses, it's going to square negative 4 and then it's going to square 4 and then stick a negative to the front of it. So it would say negative 16, but that's not correct. We need to put parentheses around our negative 4 and then say that that is what we're wanting to square, because negative 4 times negative 4 is going to be a positive 16. So negative 4 to the 4th is going to be 256. Negative 4 to the 3rd power is going to be negative 64. Negative 4 squared is going to be 16. Negative 2 times negative 4 is going to be a positive 8. And then the plus 8 just stays the same. Again, then combining all of those, we should get 896. So again, you can use your calculator to evaluate those or to check yourself. Just be careful, especially with that negative, because you are going to need to put parentheses around it when you put it in your calculator. All right, so that's if we are evaluating our function at just a number. We can also evaluate a function at an expression. So notice here, so I want us to go ahead and just find this first part. I want us to get some practice before we start trying to combine things. So we're just going to find f of 3c minus 4. Now, to find f of 3c minus 4, it works pretty similar to what we did before, but this time instead of getting an actual number as our answer, we're going to have stuff that has c's in it. So, just like before, we can kind of think about it like copying and pasting. Before, we copied that 5 and that negative 4, and we pasted it anywhere that we had an x. We're going to do the same thing here, except we're going to copy that 3c minus 4, and we're going to paste it anywhere that we have an x. So instead of writing x squared, I'm going to replace that x with a 3c minus 4. And again, on the second x, I'm going to replace it with 3c minus 4. And then, just like before, I'm going to simplify. But be careful. Remember that 3c minus 4 squared is 3c minus 4 times 3c minus 4. We cannot distribute that 2. We have to FOIL it out like we did in our multiplication section by multiplying each of the terms together. Now I'm going to go ahead and distribute that 2 because that's multiplication. We are allowed to distribute that. Then we need to multiply out. So we have 3c times 3c is going to give us 9c squared. 3c times negative 4 is going to give us negative 12c. Then we have negative 4 times 3c is going to give us another negative 12c. And then we have negative 4 times negative 4, which gives us positive 16. So then we just want to combine all of our like terms. So my 9c squared is just by itself because it doesn't have anything in common. Then I have a negative 12c minus 12c, which is going to give us negative 24c. Then if we add 6c, that would give us negative 18c. Then we have 16 minus 8, which would give us 8. And then minus 3 is going to give us 5. So we would say that f of 3c minus 4 equals 9c squared minus 18c plus 5. So just like with our evaluating at a number, that's our answer. The only difference here is instead of just getting one single number, we have an expression that has c's in it. And that's okay. Alright, so next we're going to look at some of our characteristics of our graph. So it says, the general shapes of the graphs of several polynomial functions show the maximum number of times the graph of each function may intersect the x-axis. This is the same as the degree of the polynomial. So notice on our first one, we have a constant function. So something that's a constant function would be like y equals 4. That's a 4. So if I just have that it equals some number, okay, I don't have a degree because I don't have a variable, it means that it's not going to cross my x-axis. On my next one, we have something that has a degree of 1. So we would have something that looks like x plus 2. So it can cross my x-axis a maximum of 1 times. On our next one, we have a quadratic function, which has a degree of 2. So we have something that looks like negative x squared plus 3. I have a degree of 2, which means that my graph can cross the x-axis a maximum of 2 times. On our next one, we have a cubic function, so it could look something like x cubed plus 2x minus 1, and again, it can cross the x-axis a maximum of 3 times. A quartic function is going to be something that is a 4th degree. So it can cross it 4 times, and then likewise, we have something that is to the 5th. Okay. So again, the maximum number of times that an equation can cross the x-axis is whatever the degree is. So hopefully we also kind of notice, if I look at my end behaviors, so when I say our end behaviors, I'm talking about the 2 arrows that are at the ends. Excuse me. Now our first 2 are a little bit different because they're a constant and then just to the first power, but all the rest of them kind of follow a similar pattern. So notice on our quadratic, both of our ends are pointing down. On our cubic, our ends are pointing opposite directions. On our 4th degree, they're both pointing up, and on our 5th degree, they're again pointing opposite. And that's going to be true basically for anything that has a even degree, they're both going to be pointing up or down. Or if it's an odd degree, then they're going to be pointing opposite directions. Now, let's look at how we might write that out. So, when I'm looking at the ends of the graphs, notice that we have a left side and a right side to our graph. So we need to talk about both sides. Now, if I'm wanting to talk about the left side of my graph, notice that if I'm going to the left, I'm talking about x as it goes towards negative infinity. The little arrow means goes towards. So I'm saying x is going towards negative infinity. I'm talking about the left side of my graph. If I'm talking about the right side of my graph, it's basically going to be the opposite. Notice the farther that we go right on our x-axis, x is going to be going towards positive infinity. Likewise, on each of my sides, notice that our graph is either going to be pointing up or pointing down. If it's pointing up, we're going to say that f of x is going towards positive infinity. And if it's going down, we're going to say f of x is going towards negative infinity. So basically, you're going to pick the two that are true. If we're talking about the left side and it's pointing up, we would say f of x goes towards positive infinity as x goes towards negative infinity. If we're talking about the right side and it's going down, we would say f of x goes towards negative infinity as x goes towards positive infinity. Basically, you're just picking the two for whatever situation is true. So, I have a couple of examples here. So notice on this one, both of our ends are pointing up. So f of x is going towards positive infinity on both of them. So we say f of x goes towards positive infinity as x goes towards negative infinity. And then also f of x goes towards positive infinity as x goes towards positive infinity. Likewise, on my next one, notice that we're pointing down on the left-hand side. So we would say f of x goes towards negative infinity as x goes towards negative infinity. And then it's pointing up on the right-hand side. So we would say f of x goes towards positive infinity as x goes towards positive infinity. And then basically we have the opposite on our third one. They're both pointing down. So both of my f of x's are going towards negative infinities. And then on our last one, it's basically the opposite of our graph above. So I want to make us a little chart that's going to help us decide what the end behaviors are going to look like. Now, notice that on our first one, I have an even function. So remember that if it's an even function, so that just means that I have an even degree. Your ends are the same. If I have an odd function, or in other words, I have an odd degree, your ends are opposite. So think odd, opposite. Now, to determine whether they on our even function, so let's say even. So you first need to decide if it's an even function or an odd function. And that tells us if we want to use the top row or the bottom row. From there, we need to decide what our leading coefficient is. So remember that your leading coefficient is just going to be the number that's in the front of your first term. So if your leading coefficient is positive, then if I have an even function, both of my ends are going to point up. Let's use a different color so we can kind of tell the difference. Both of my ends will point up. If it's an odd function, remember they have to be opposite, so the left side points down while the right side points up. Now, if my leading coefficient is negative, basically it's just going to be the opposite of those two. So if it's even, both of my ends point down. If it's odd, the left side will point up, but the right side is going to point down. So basically, anytime that you want to know what your end behaviors are going to look like, you need to know is it even or odd, and then you need to know what the leading coefficient is. So it says label the following graphs as even or odd functions. Again, we're going to look at a couple of things. We want to, 1, look at how many zeros we have. And then 2, we want to look at our end behaviors. So notice on our first one, we have 0 zeros. So it could actually be any function or any degree, because remember that your degree is just the maximum number of zeros that you have. You can actually have any number below that. That's just the maximum. Well, since we have 0 zeros, it could be any number. But notice that both of our ends point down. So that means that they're doing the same thing. So that means that we have to be even. On our next function, we have 4 zeros. So we know that our degree has to at least be 4. Now it could be something above 4, but it would have to at least be 4. But again, notice that both of our ends are pointing down. So again, it would be even. Now notice for both of these, our leading coefficients would be negative because they're both pointing down. On our next one, notice that I have 1 0, which means that we at least have to have a degree of 1, but that our ends are pointing opposite directions. So this tells us that it's going to be an odd function. On our next one, we have 3 zeros, so it at least has to be a degree of 3. Again, they're pointing opposite, so it's going to be odd. This time, though, notice that for our first one, I'm pointing up on the left and down on the right, so our leading coefficient would have to be negative. On our second one, we're pointing down on the left and up on the right, so the leading coefficient would have to be positive. So it says, for each graph, describe the end behavior, determine whether it represents an odd degree or an even degree, and state the number of real zeros. So just kind of combining all of the characteristics that we've been talking about. So notice that on part A, we would say f of x is going towards negative infinity because it's pointing down. And since it's going to do that on both the left side, which would be as x goes towards negative infinity, and the right side, which is as x goes towards positive infinity, I'm just going to go ahead and say it goes towards negative infinity for f of x as x goes towards positive or negative infinity. Now, for our second one, notice that on the left side, f of x goes towards positive infinity, is pointing up. So we need to say that it goes towards positive infinity as x goes towards negative infinity. And then f of x, it's pointing down, so we say negative infinity, and it's on the right side, so we would say as x goes towards positive infinity. Now on our left-hand one, let's count our number of zeros. I have 1, 2 zeros. And notice that our ends are pointing the same direction, so I know that this has to be an even function. On our next one, we have 1, 2, 3, 4, 5 zeros. And our ends are pointing opposite directions, so we know that it has to be odd. Now, another thing that we can find on our graphs are called relative minimums and maximums. You've probably looked at mins and maxes before, but when you looked at mins and maxes, you were looking at just like the biggest point of the entire graph or the lowest point of the entire graph. We're going to be looking at relative maximums. So, for a relative maximum, it is a point with the greatest y value of any nearby points. Now I put nearby in quotation marks because nearby doesn't really have a mathematical definition. The problem though is that in order for us to give a very, very accurate definition, we would have to use mathematics that's above our level at this point. So basically, we're just going to look at if it's a maximum point or if it's the highest point of anything that's kind of close to it. Likewise, a relative min is going to be a point with the smallest y value of any, again, nearby points. And your relative extrema is just another word for saying all relative minimums or relative maximums. These are called turning points because it's where the graph is going to turn directions. So when we look at an example of these, it might make a little bit more sense by what I mean by relative or nearby if we think about it in terms of my graph is turning directions. So let's look at an example. So notice on our first spot, it says I have a relative maximum. So let's use purple. So this right here is going to be a relative maximum. So notice that it is the highest point of anything kind of around it. It's the biggest y value of the stuff that's close to it. Now notice on the other side of the graph, I have points that go up higher than that point, but I only want to look at the stuff that's kind of around it. Or, like I said, notice that our graph kind of turns and goes another direction. Likewise, we have a relative minimum. So it is the smallest point of anything around it. Or again, it changes direction. And when I say direction, we can kind of think about that what's called increasing or decreasing. So when we're talking about polynomials, we're talking about things that have degrees that are larger than 1 most of the time. So we're not going to have just a line, we're going to have a curve. So unlike when we have a line, we can talk about slopes with lines because our slope is constant, it's the same thing. With our curves, we cannot talk about slopes because the slope is ever changing. Sometimes we could be going up faster, sometimes we could be going up slower, and that can all depend on which part of the graph you're looking at. So you need to be careful that we can't talk about slope, but what we can talk about instead is if it's increasing or decreasing. So a graph is going to be increasing if y values get larger as x values get larger. So if I'm talking about x values getting larger, I'm talking about going towards the right. I can't just say it goes up, because up is kind of relative, I need to give it some sense of direction. So I'm going to say as my x values get larger, that way I know I'm talking about going to the right. Likewise, I know that something is decreasing if my y values get smaller. As x values get larger. So again, I'm going to the right, but this time my y values are going down or getting smaller. So notice on the graph that we have, our graph is going to be increasing, or in other words, as we go to the right, we're going up. So this portion of the graph is increasing. However, notice that as we go to the right, we're also getting bigger y values on that last portion of our graph as well. And then lastly, we are decreasing or going down in that middle portion, or basically as we go to the right, our y values are going down. So let's kind of take everything that we've done and combine it all together. So it says, determine the following about the given function. So I have a nice pretty graph there. It kind of cut it off a little bit at the end, but we're going to assume that it continues in a similar manner. There we go. So it says the x-coordinates of our turning points. So when I'm looking at my x values, I'm looking for my turning points. So notice that we have 3 turning points. I have a turning point here at the top. I have a turning point down here at the bottom. And I have a turning point here kind of in the middle. So if I'm just talking about the x values, I have a turning point at x equals -2. I have a turning point at x, we're going to assume that it's at 1, and we also have a turning point at x is approximately, well, it's like 2.5. So notice that we have 2 relative maximas and 1 relative minimum. So we have a turning point. So remember, every turning point either has to be a relative max or a relative min. If I turn directions, I know I have to have a relative min or a relative max there. So we would have a relative maximum at that first point, which would be -2, 4. Our other point, which was at the 2.5, would also be a relative max. And we're going to say that it's at negative, let's say 1.5. Alright, and then we have a relative min at that 1 comma. We're going to say that it's at -5. Okay, now we're going to look at, okay, my x coordinates of my zeros. So we have 1, 2 zeros. So we're going to say that we have zeros at x equals, let's say it would be -3, let's say 0.5. Make it easier on ourselves. And then we also have a 0 at -0.5. So we have 2 zeros. So because we have 2 zeros, we know that the smallest possible degree is going to be 2. So then we also need to state are intervals of increasing and decreasing. So notice that we would be increasing. And when we talk about increasing and decreasing, we're going to be talking about x values. So we're going up or getting higher y values as we go to the right from the beginning of our graph. So we're going to go ahead and say that that is negative infinity. And notice that we stop increasing at that turning point, or at that first relative max, which is at -2. Well, then notice that we are also increasing when we go from, again, we're talking about x values, so from 1 to what we decided was 2.5. Then notice that we are decreasing basically on the opposite spots. So we are decreasing from -2 to, we get to 1. And then we're also decreasing from that 2.5 until we get to infinity. So we have 2 intervals that we're increasing and 2 intervals that we're decreasing. Now our last 2 things, we want to look at the domain, and that should say range. So notice that I have arrows on both the left and the right hand side, which tells us that we're going on forever. And because we don't have any holes or breaks or jumps in the graph, we can say that this is all real numbers. Now, because both of our ends are pointing down, we know that we can be any y value that goes down forever. So it could be -2, -100, -5 million. It goes down forever. But as we continue up our graph, notice that the highest y value that we get to is 4. And since we're assuming that those arrows indicate that we're pointing down forever, we're going to say that our range is from -infinity to 4. So remember that this is called interval notation. So I'm saying that it is from -infinity all the way until I get to 4. And I need a hard bracket or a square bracket around 4 because we include 4. So the other way that we can write this is with set builder notation. So we would say y such that y is less than or equal to 4. Basically, if I can put an equal to bar on my interval, then I get a square bracket. Now, because I can never technically equal negative or positive infinity, our infinity symbols always get parentheses.